Good morning, everybody. This is Nicolas Barras. We continue our lectures on statistical computing and machine learning. And today we're going to start a new class of lectures about Monte Carlo methods. So usually this is not a topic you cover in detail in machine learning courses. However, since we're all interested in scientific applications, Monte Carlo methods are a key ingredient of many machine learning techniques for complex systems, for the implementation of complex systems. So I feel that it is essential to spend a number of lectures reviewing Monte Carlo methods, both from theoretical but also from a practical and algorithmic point of view. Okay, so let's see the type of topics that we will be covering in this lecture today. So we will review first why do we need approximations like Monte Carlo methods, and we will go back to review some of our fundamentals in Bayesian inference and see where Monte Carlo methods can be helpful. We will discuss about Monte Carlo estimators and their convergence properties, some of their limitations in high dimensions. We will introduce what's called the sample representation of a distribution that it will lead to the sample representation of Monte Carlo estimators. And then we will see a number of examples, try to relate Monte Carlo integration with deterministic integration. We will see how to compute integrals in high dimensions, how to compute Bayes factors, and a few other examples on passing. A little bit about the references. There are many excellent textbooks and resources on the web that you can find on Monte Carlo methods. The textbook by Robert and Casella on Monte Carlo statistical methods, it's fantastic. Strongly recommended to have it in your library. The textbook by Liu on Monte Carlo strategies for scientific computing has lots of modern ideas as pertain to applications in biology and the sciences. We already have seen applications of Monte Carlo methods in the Bayesian core book. And finally, there is a lot of web resources by Professor Doucet on statistical computing and Monte Carlo methods, and significant part of our lectures extracts elements from this lecture note. So I strongly recommend that visit the various resources available on the web. Okay, so the goals for the lecture today will be to understand the use and convergence properties of the Monte Carlo estimator, how we can calculate integrals of any forms, not just forms that directly point to computing expectations. We will discuss about the sample representation of a distribution, the differences between Monte Carlo and the integration you have seen in calculus. And of course, we're going to try to see that not everything is rosy, and there are significant limitations of Monte Carlo estimations in high dimensions. And I will finish with some examples, including one that we compute the Bayes factor using Monte Carlo. Of course, if you remember, the Bayes factors are nothing else but the ratio of the marginal likelihoods between two models. So the fact that the marginal likelihood involves integration in the parameter space is not surprising that it would lead to eventually the use of Monte Carlo methods to perform those integrations. Okay, so let's review where Monte Carlo comes in the context of Bayesian inference. So if you look at the posterior of some parameters theta given some data x, okay, you notice that most of the applications we have done up to now, especially using conjugate priors, this posterior was analytically computed, and that was the end of the story. But in many occasions, maybe because the likelihood model is a computer code, this posterior can only be implicitly used, especially can only be used with samples that can be drawn from this distribution. But somehow we need to be able to do calculations with this posterior when it is not analytically available, and Monte Carlo is going to be helpful. Also, you can see in the denominator there is an integral, and this integral requires an integration in theta. And if you do have a high dimensional parameter space, then that integration cannot be performed analytically. Now, once you have the posterior distribution, even talking about point estimates, like if you want to compute the posterior mean or the variance, each term that you see in these equations involves integrals, and these integrals, again, in high dimensions, need to be performed with Monte Carlo estimation. Now, even computing the mode of the posterior, that obviously requires an optimization problem, that problem itself can be performed with Monte Carlo methods, and I'm going to give you an idea on how to do this when the posterior is written in terms of samples that are drawn from this distribution. Okay, so we will see this shortly. And eventually, you remember when we talked about hierarchical models, if you have, let's say, some parameters theta that consists of theta 1, that depends on theta 2, that etc. depends on theta 3, you may have to do marginalization of parameters that you don't need, and that marginalization to compute, let's say, the marginal posterior of theta 1 requires an integration in theta 2, and that again can be performed with Monte Carlo methods. Okay, so let's see some other examples. How about the predictive distribution? So if we have the posterior of theta given some data x, and now we want to compute the predictive distribution of y. So this is the probability that we will see in the future y after we have observed x. This requires, if you concentrate, so the first, if we look at the predictive distribution, it's nothing else but this integral of the likelihood times the posterior with the parameters integrated out. So that by itself requires, generally speaking, a Monte Carlo approximation. And if you look at the mean of the predictive distribution, that's a double integral both in the parameter space and also in over the different values that y can take. So again, the predictive distribution can benefit by Monte Carlo. And finally, this large scale of problems that we discuss about model selection can also be performed with Monte Carlo methods. And here I give you the joint distribution for model k and the corresponding parameters for model k that I call theta k. So what you see in the numerator is the likelihood for model k times the joint prior of k and theta k. So really what the second term is, that's the prior of theta k of theta given the model k. So I'm putting this with subscript p of k theta k. That's the prior of model k. And then on the denominator you have this high dimensional integral that requires summation over models, but also for each model integration over the parameter space. So again, a lot of these calculations can be performed, especially in high dimensions with Monte Carlo. Okay, so Monte Carlo basically will allow us to compute this high dimensional integrals, and this is what the lecture today is going to try to cover to some extent, even though most of the examples that we will see will be not in high dimensions. So let me go back and review the very basic example that we saw very early on when we were talking about the law of large numbers and the central limit theorem. If you remember, we were conducting an experiment where we wanted to get an approximation of pi, and the way we did this, we considered this square from -1 to 1 in both directions, and the circle of radius 1 inside the square. I call the circle here calligraphic D, I call the square S, and we were trying effectively to get the area of the circle, by throwing, if you like, darts inside the square S, and counting how many times those darts, target basically the area inside the circle D. Okay, how many times these darts are landed inside the circle D. So that helps us to get an estimation of pi. So we're going to revisit this and see formally how these calculations are related with Monte Carlo methods. So let me first define a random variable d that consists of these x and y, which are the locations in which a dart that I'm going to throw in this square is going to land. Okay, so d is a random variable, and I'm actually going to take it to be a uniform random variable defined on this square from -1 to 1 in both axes. So if I want the probability that that d belongs in a central, in a certain part of the domain A, really this probability is nothing else but the area of A divided by the area of the square. Okay, so in our case, if we want to compute the probability that we will land inside the circle, this probability is nothing else but the area of the circle divided by the area of the square. So what we will do is we will throw a dart n times, and we're going to collect the realizations of these random variables d1, d2, dn, which are the coordinates x and y for where each dart is landed, and you can see those with little dots given inside the square. And of course we're going to assume that all of these are IID random variables. Now you anticipate, okay, based on the discussion we have seen when we we formally introduced this problem many lectures ago, that somehow the probability that you will land, let's say, in the circle is the times, in these n experiments that you did, is the times that the dart landed inside the circle A divided by the total number of you throwing this dart on the square. So the question now that comes is, where is this result coming from, and is there any statistical interpretation of this common sense answer that you see there? So is there any statistical interpretation why the probability that you will hit the circle is the number of times that the dart landed inside the circle divided by the total number n of this experiment where you're throwing the dart on the square? So let me see this briefly, how we're going to do and formally see the statistical interpretation. So the first thing I'm going to do is I'm going to introduce an indicator function. And I remind you what's an indicator function. So in this case, my indicator function takes as arguments x and y. That's the location where the dart is going to land in the square. And there is a subscript here, a. So if x and y are inside A, the indicator function is 1, otherwise the indicator function is equal to 0. Now, with that said, if you remember, the probability that I will land in the circle is the area of the circle divided by the area of the, of the square. And notice what I'm doing here is I am writing the area of the circle as the integral over the square now of the indicator function. Now you can actually see immediately that this is equal to the area of the circle because the indicator function is 0 outside the circle, and otherwise is 1, so that way this integral is going to become the area of the circle, but I will keep it like that, right? So I will keep this integration on S of the indicator function, and this whole integral is the area of the circle. Now, this dx dy over the square is the area of the square, which is 4. And now I have this nice expression that says is an integral over the square of the indicator function times 1/4 dx dy. Okay? And if you want to see the proof that this is the area of the circle, again, it is given on the bottom, but there's nothing really major that you need to worry. So this is what we derived. All right, so the probability that we will land in the circle is the integral of the indicator function times 1/4. Okay, now if you think about what 1/4 is all about, we said that we're throwing these darts on the square uniformly. So really the probability that is affiliated with our experiment is 1/4, okay? Because the sides of the square are from -1 to 1 and -1 to 1. So effectively, what under the uniform distribution, what you see here is nothing else, if I can go directly on the bottom of this equation, but the expectation with respect to the uniform distribution of the indicator function I subscript a of x and y, that simply here I call v of d, where d is x comma y. I don't really need to have extra variables, but somehow I just to simplify things so I don't carry the indicator function with me all the time. So v of d is nothing else but the indicator function we have before. So effectively this formula that you see on the top, it is nothing else but the expectation of this random variable with respect to the uniform distribution. And immediately you can start thinking, if you have an expectation with respect to any distribution, you can approximate this expectation with a sample mean, and the sample mean will be the sum of the values of the indicator function at the n experiments divided by n, and that immediately gives you the number of times in your n experiments that you landed inside the circle divided by n. Okay, and we will see this again in one slide or two, but before I do that, let me just remind you, for those who forgot, the strong law of large numbers. So if you draw samples xi from some distribution that has a mean mu and a variance sigma square and a finite variance, then the sample mean asymptotically becomes the true mean of the distribution almost surely, and that's the strong law of large numbers. And then of course we show the weak law of large numbers. So if you conduct the same experiments and you take your sample mean, as n goes to infinity, the sample mean converges to the true mean from where these samples are coming. And of course you can write this in many other different ways. So for example here, what I'm doing is I'm writing the probability of the absolute value of xn minus mu being greater or equal than epsilon. So I am saying for every epsilon, the probability that I will be away, that the sample mean will be away from the true mean by epsilon on the limit of n going to infinity is equal to 0. Okay? So you can take epsilon to be as small as you want, but as n goes to infinity, this probability eventually will be 0. Okay? So again, all of these are manifestations of these strong and weak laws of large numbers. And of course, we went a little bit further, and we show, by the way, you see in the equations on the bottom that the expectation of the sample mean is the true mean, and the variance of the sample mean is sigma square over n, where sigma square is the variance of the distribution from where I'm drawing data. Okay, so remember this. So we have extended this laws of large numbers with the central limit theorem. The central limit theorem is basically can be summarized, if I can go down just in one of the forms that you can remember, the other ones are equivalent. So as n goes to infinity, the sample mean basically follows a Gaussian, a normal distribution with mean the true mean of the distribution, and a variance that is sigma square over n. What is important here to remember, right, and pay attention is that it doesn't really matter from where the samples xi come, what type of distribution. The idea here is can be any distribution, and even in that arbitrary distribution, when you form the sample mean is asymptotically, basically it comes from, it's a sample from a Gaussian distribution with mean, the true mean, and the variance sigma square over n. So before we go to this square and circle experiment and the dart throwing experiment, let me just mention something about indicator functions. So indicator functions take the values 1 and 0, and in the way that I defined before the indicator function, it was are my xy's inside the circle or they're outside the circle. So the value was 1 and 0, which means if you try to compute the expectation of an indicator function, and you can think right now, even though the slide is more general, you can think the indicator function that represents being inside the circle or outside the circle. So you can see that because this variable is binary with values 1 and 0, that the probability that you will actually hit the circle is the same as the expectation of this random variable. So when you see me in the slides sometimes writing the expectation as the probability that I will hit the circle, just remember that the two things are exactly the same, simply because my indicator function is a binary variable by definition. So let's go back to this experiment of throwing the darts inside this square uniformly. You remember I took these samples that they are these indicator functions for different locations di. So these are x, y, yi locations that I'm throwing the dart, and then from the law of large numbers, we know that if we take the sample mean of these v's, so this is the sample mean basically of my indicator function realizations in my n experiments, then this empirical average, it will actually be asymptotically an approximation of the true mean of my distribution, and the true mean is basically that I will hit the circle, right? That is the true mean in the experiment that we're conducting. Okay, so effectively what we have is formally I can write this with this equation that as n goes to infinity, this empirical average converges to the expectation under the uniform distribution of this random variable v, where v corresponds to throwing the dart to an arbitrary location x and y inside the square, and v again, remember, are indicator functions which are either 1 if I'm inside the circle, or they are 0 if I am outside the circle. So this Sn, as n goes to infinity, approaches the true, approaches this expectation. And you remember the expectation, because the v is a binary variable, is the same as the probability that I will hit the circle, and the probability that I will hit the circle is pi over 4, right? Because the area of the circle is pi, the radius is 1, and the area of the square is 2 times 2, so it is equal to 4. So in many ways, I can write the following, that Sn is pi over 4, which is the true value, plus some error term. Right? So you can think of Sn being an approximation of pi over 4. And the question that we will need now to address is, how good is that approximation? So if you conduct this experiment n times, can you say something about the error that you do? And the answer is, yes, you can, because we know that the variance of the estimator can be computed, and it is nothing else, right? We saw this before, but 1 over n, the variance of v, okay? So that's the, if you are throwing the dart on some arbitrary location x and y, and v is your indicator function that you'll be on the circle for that x and y. So the variance of v divided by n is the variance of your estimator, okay? So where is the n coming, right? When you remember Sn is the summation of this vi's divided by n. So when you take the variance, you get 1 over 1 over n squared times the summation of this, which are iid. So this will give you n, and one of the n's will cancel out. So you have 1 over n times the variance of V. Okay, and you can actually think, if you take the standard deviation, that the standard deviation is the square root of variance of V divided by the square root of n. And this is our first time that now we can see that the error of the Monte Carlo approximation, it is actually decreases as 1 over square root of n. This is extremely important, and this is something you need to remember, that the error of your Monte Carlo approximation decreases as 1 over square root of n. Now, in our case, the variance of V, we can actually compute it analytically, and because I already told you that the probability that you will hit the circle is pi over 4, and that is the same as the expectation of V, and of V squared as well. So you can actually compute the variance of V to be this nice number. And again, remember, the variance of V is the expectation of V squared, which is actually the same as the expectation of V, which is the same as the probability that you will hit the circle, minus the expectation square, so you get this nice number. In other cases where you cannot compute the variance of V, analytically, we will see how to approximate this with Monte Carlo, and you can actually start guessing that the approximation would be nothing else but the sample variance. So you can compute this directly from your samples. Okay, so let's see some nice properties of this estimator. In the context of the central limit theorem, you know that Sn, in a distribution sense, you will approach a Gaussian distribution with mean, the true mean, and a variance that is the variance of V over square root of n. And then, you know what, you can start computing various inequalities that will give you the probability of being away from the true mean by a certain amount, and you can actually do all of these computations using tables of the CDF of the standard normal. So I am not going to spend time discussing all of this in detail, but for example, here is a nice inequality that you can get directly in terms of the values of the standard normal. So phi, capital Phi here, is the CDF of the standard Gaussian N01. So this gives me the probability that I'm going to be away from the true mean by 2 times the standard deviation. All right, that's the error that of the estimator. So the probability that we will be 2 times the standard deviation is 0.0456, and that is an exact number. And again, this is for our dart throwing experiment, and this is our estimator in essence of pi over 4. We can write more inequalities like this. So for example, for any n greater or equal to 1, and for any epsilon, the probability that you will be away from pi over 4 by epsilon, you can write it down as in terms of this value of the CDF of the standard normal, and this whole term, you can simplify it as the complementary error function for this argument. And then actually for, as n goes to infinity, you can consult Wikipedia for error bounds of the complementary error function, and you can have this useful, potentially useful bound for this error. Okay, so effectively, this is a very useful inequality, right? So it tells you the probability of being away by epsilon for any epsilon, and is given by this for any n that is greater or equal to 1. Now, if you search the literature and you look at statistical and probability books, you will see many other inequalities, and maybe in passing, when we generalize this, I'm going to give you 1 or 2 additional bounds. So let's wait, let's return on the, for now, to the dart throwing experiment and compute what's called the coefficient of variation. And if you remember, when I discussed about variance, I had introduced the coefficient of variation. And in our case, the coefficient of variation is the standard deviation of my estimator. All right, that's the standard deviation of my estimator, and that is, you remember, the square root of pi over 4 times 1 over pi over 4 divided by n, square root the whole thing, okay? And then the expectation of Sn, which is the probability that I will hit the circle, is pi over 4. So this is the coefficient of variation, and if you want different values of the coefficient of variations, this is the number of samples that you need, and you can see that not everything is very rosy. If you want a very small coefficient of variation, it's not surprising that the number of samples has to increase to the value that you see there, 2,739, okay? Now, one way or another, looking at the coefficient of variation, looking at the standard deviation that we saw before, the error that you do in the Monte Carlo approximations here, it decreases as 1 over square root of n, and that's something that I want you to remember. So let's see one or two more inequalities that capture the error of the Monte Carlo approximation. And here is a bursting inequality, extremely useful. It says the probability that I will be away by epsilon from the true mean is bounded by 2 times e to the minus 2n epsilon square. Now, you can appreciate that the tighter these bounds are, the more useful these inequalities are, because if I tell you the probability of this is less or equal to 1, or less or equal to infinity, that is not going to be of any use. But here, for any n and for any epsilon, I can write this inequality, and that's the bursting inequality. And actually, using this result and plugging in different values for epsilon, you can modify it, and you can write the following, that the probability that you will be away from the true mean by epsilon, that probability being less than alpha. So if you want the probability to be smaller than a given number, then the number of samples that you will need is given by this bound here. So n needs to be greater or equal to the log of 2 over alpha divided by 2 over epsilon squared. And actually, if you use this inequality and you put a particular value for epsilon, which is this square root of the log of 40 divided by 2n, then this probability that you'll be away from pi over 4 by this number is less or equal to 0.05, regardless of the value of n, assuming n is greater or equal to 1. Okay, now you can appreciate again that looking, for example, in the last inequality, that the error of this approximation is always inversely proportional to square root of n. So let me throw a few trivial simulations of the pi over 4 estimation. So what you see here is you see the convergence. So you see the error basically of Sn minus pi over 4 as it converges for different values of the samples n. If you repeat this continuously, this is what you get, okay? These are 100 realizations. And again, these realizations, remember that the error for every given n that you do is plus minus 1 standard deviation, that is the variance, the square root of the variance of it divided by the square root of n. And so you have those two bounds basically for any given n, and they are shown here with dotted lines that I think you will need to zoom this picture to be able to see them. Okay, this is a duplication of a schematic from the Bayesian core textbook for exactly the same example. So again, this schematic provides an estimation of the area of the circle, and the area of the circle is actually nothing else but the number of counts, this empirical count that we had before, that you will hit the circle, multiplied by the area of the square, that in our case is 4. Okay, I am not going to go to any details here, but so let me concentrate that you can compute the true error of the estimator, because we know the variance of V to be this pi over 4 minus pi over 4 square. So this whole thing gives you the plus minus 1 standard deviation of your estimator. That's an exact estimate, but actually you can also compute this numerically, and it's a good idea to know how to do this, because very often you will not know analytically what this variance of V is. So numerically, how do you compute? You have your samples from this n different locations that the dart landed inside the square. So you compute this square error of the indicator function of this xj, yj, and of course you will need an approximation of the mean, and the mean is given by Sn. So so this 1 over n minus 1 times the sum of squares, that's the unbiased estimation of the variance, all right? And that's the variance of V, all right? And the variance of the estimator, you remember, is the square root of the variance of V divided by n. So so when you see 1 over n times 1 over n minus 1 and the whole thing square root, remember 1 over n minus 1 comes from the sample unbiased form of the sample variance, and the other 1 over n comes from your Monte Carlo approximation. Now, so in this picture, the color regions are computed with the numerical error bars. These horizontal lines are the analytical error bars, and you can see things look to compare very well. But also keep in mind that in the plots that are shown here, the experiment was repeated capital S times, and then the values of the estimator were averaged over those capital S values. Okay, let's keep going. And the first thing we need to discuss is how are these things can be extended to high dimensions. So instead of having a circle and a square, how about if we had a hypercube and we had a hypersphere inside the hypercube? So obviously the dimensions now of the problem are getting very high, because n theta is, let's say, 1,000, is much higher than 1. So what exactly is going on? So the first thing, let me just tell you that the derivations that we did, nothing changes. Still, you will work with the indicator function that you will hit the hypersphere when you're throwing your darts inside the this hypercube. And it turns out everything we did is also valid in this particular case, and the convergence, and this is the interesting conclusion, is exactly 1 over square root of n. So it the estimator converges as 1 over square root of n, so it is independent of the dimension of the problem n theta, and that is a very fundamental property of Monte Carlo estimations that you need to keep in mind. Now, if we were to do this problem deterministically by using a uniform grid in each of these directions n theta, then trying to compute the area of this hypersphere, it will give you a convergence that depends on the dimension of the space. So you can see the order of convergence is 1 over n to power r divided by n theta, where r in general has to do with the smoothness, in this case, of the hypersphere, or whatever sub area inside this hypercube you're looking at, okay? And n theta has to do with the dimension that you're looking at. So you can see that the convergence for a given n, the convergence of this deterministic approach for computing the area of the hypersphere decreases with the dimensionality n theta, and the Monte Carlo estimator does not change at all as with n theta. It is independent of n theta, and the order of convergence is 1 over square root of n. So let's see this in practice, because we're talking about this hypersphere and hypercube. Let's indeed consider a unit hypercube, all right? And we take the sphere inside this hypercube, and when I talked in a lecture on the scarce of dimensionality, I gave you the equations for the volume of the unit sphere that you see here. And the only thing I remind you is that this volume goes to 0 as n theta goes to infinity, because you remember most of the volume in a high dimensional hypercube is in the surface, and it's actually in the edges of the hypercube. So when you try to conduct these dart throwing experiments in n theta dimensions, is like you're trying to hit the sphere that is of infinitesimal volume, all right, in a hypercube that has a volume that is 2 to the power n theta, right? So we take that every side of the hypercube is from -1 to 1, so the volume of the hypercube is 2 to the n theta, and the volume of the sphere as n theta goes to infinity is equal to 0. So what is the estimator going to give us? Everything we have discussed up to now will remain the same. The only thing is that the probability of hitting this hypersphere in high dimensions will be different, and also the variance of our samples V, or I think I call them here X, will be different here as well. So let me just give you the variance for the Monte Carlo estimator will be the probability that we hit the hypersphere minus this probability square. And because P, we just said, since the volume of the hypersphere is very small, P squared is much smaller than P, so this becomes P over N, okay? And this probability P is nothing else again but the volume of the hypersphere divided by the volume of the hypercube, okay? So that's the only thing that changes, this P of n theta, and the convergence again being of the order of 1 over square root of n remains exactly as what we had before. So let's do the following thing. Let's compute the coefficient of variation. So I'm going to take the error of my estimator divided by the expectation, which is this probability that I would hit the hypersphere in n theta dimensions. So I get this nice result. And now observe what happens. Let's say that you want this coefficient of variation to be a small number, let's say 0.1. So for this to become 0.1, immediately you can see that n has to be 100 times 1 over this probability. So that's when the coefficient of variation is 0.1. So let's evaluate what this number is all about. So for, let's say, 20 dimensions, if you use the formulas I gave you before on the previous slide for the probability that you will hit the hypersphere, and you do the algebra and you calculate the gamma function that comes in the volume of the this unit hypersphere, it turns out that the number of samples that you will need to get a coefficient of variation 0.1 is now 10 to the 9th. So that's, of course, a huge number that tells you that working with Monte Carlo in high dimensions, at least working with vanilla Monte Carlo, has its own challenges, and somehow you will need to think carefully on how to go about and what type of Monte Carlo approximations you will need to do to make this reasonable in high dimensions. Okay, as I mentioned, for this particular example, the fact that you need so many points has to do with the volume of the hypersphere being infinitesimally small, and the volume of the hypercube being huge, but that huge volume is mainly on the surface, so the sphere still appears to have very small volume. So it's trying again to throwing darts to hit this practically zero volume hypersphere when all the volume is near the surface of the hypercube. Okay, so let's generalize this Monte Carlo estimation. So actually, this slide that you see here, there's nothing new here. It it indicates that if the variance of x, and interpret x here again, this indicator function that you will hit, let's say the hypersphere, if that is of the order of c times some number alpha to the dimensionality of the problem, then if you want the variance of your Monte Carlo estimated to be less than epsilon, you can see that the number of samples, it's exponential in the dimensionality of the problem. Okay, that's sort of a generalization of what we saw in the previous slide. Okay, so let's try to generalize what we have seen for the circle experiments. So let's say that so before you remember we took samples by throwing this the dart on this square. But now let me generalize this, and let me say that I'm taking samples from any distribution pi. Okay, before those samples were coming effectively from a uniform distribution defined over this the square that we had. But let's take, say, samples theta I from any distribution pi, and let's say that we want to compute the probability that theta is in some domain A of my sample space capital theta. So think this being our square before, A being the circle, and I'm asking what's the probability that that I will hit the circle. But we generalize this by asking what's the probability of A, where A is a subset of theta, and obviously the estimator, by extending the ideas from this throwing of the dart experiment, P of A will be the number of samples in A from my n samples divided by the total number of samples, and by the law of large numbers. All right, this empirical estimator that we have here, the sample mean of this indicator functions computed at each of the samples theta I, asymptotically as n goes to infinity, is nothing else but the expectation with respect to pi of the indicator function I subscript A of theta. Now, where is this coming, right? If you think about this expectation, this will be an integral over the domain theta of this indicator function times pi of theta d theta, and this indicator function is only non-zero inside A, so effectively what you get is you get pi of A. So if you want to compute the probability pi of A that theta is in A, then this number of samples that are in A divided by the total number of samples gives you your Monte Carlo approximation, similar to what we have done with the dart throwing experiment. Okay, so lots of these things that we discussed before, of course, can be generalized. And here, for example, if you want to calculate an expectation like that, all right, you may ask, can I do this expectation with Monte Carlo? The answer is yes, right? What you can do is you can take n samples from the distribution pi of theta, and then you can use the empirical mean of f computed at each of the theta i's, and that, according to the law of large numbers, will give you an approximation of the integral that you see here. And all of this again is with the assumption that this integral is finite. Okay, so let me I'm going to click all the results that they're identical as before. So the estimators for the integral will be what you see here, will be this unbiased estimator. Using the law of large numbers, it converges to the true mean, and we know what the variance is. The variance of this is the variance of f of theta under the pi distribution divided by n, and from the central limit theorem, we know that in distribution sense, this estimator follows a Gaussian with mean the true mean, and the variance being the variance of f divided by n. So there is nothing, again, the equations look identical with what I had in this dart throwing experiment, but now we're using this to calculate the expectation of any random variable f of theta under the distribution pi of theta. So basically that integral f of theta pi of theta d theta, NSN is just the Monte Carlo approximation of that integral. Now if you pay attention to the details on the slide, to be able to implement this you need two things, right? So you need to be able to take samples from the distribution pi, so that will take us several lectures in our Monte Carlo series of lectures. And second, you need to be able to evaluate this function f at each of the samples. But beyond that, the procedure is what you see on the slide. You know, it converges to the true expectation of f of theta, and you know that the error, the variance, is this variance of f of theta divided by n. Okay, so again, we need to be able to take samples, and we need to be able to evaluate this function f for each of the samples. So let me just give you some pictures of now on. So let's say you take samples from a distribution pi of theta, and I would like you to start thinking if somehow these samples can be used indirectly to approximate a distribution pi, and the answer is yes, they can. So before I show you a schematic, let me remind you what a delta function is, right? If you try to integrate f of theta with this delta function centered at theta 0, you know that you get the value f at theta 0. So this delta function is this huge spike that goes to infinity, but once you integrate it, you effectively get the value of the function at theta 0. So what I want to do is, if I can go directly on this, okay, I want to compute, I want to start with a mixture of delta functions, each component being a delta function centered on the samples theta I that that came out of a distribution pi of theta. So I call this mixture of these delta Dirac functions, I call this the empirical distribution, and I denote it as pi hat subscript n. So pi hat, that it is an empirical approximation, and that I have n samples, and you notice each of my samples, or each of these delta functions, has the same weight that you see here as 1 over n. Okay, so I have an empirical measure that is denoted like this, and now what I want to ask is, I want to know if I compute with this empirical measure the probability pi hat of A, right? Before, if you remember, we computed pi of A, all right? Pi of A. So now what I want to do is I want to compute this integral that you see here, that is pi hat subscript n of theta d theta. So I want to know what is the probability that I will be in A under the distribution defined by this empirical mixture of the delta Dirac distributions. So if you do the computation, and the only thing I'm doing here is I'm taking this definition of this mixture of delta functions, I'm putting it in here, and then I'm going to have 1 over n like that. And notice the integration, all right? The integration is in the domain A of interest. So if you integrate each of these delta functions, you will get 1 if theta I is inside the domain A. Otherwise, you will get 0. So effectively, its integral of delta of theta I inside A will give me nothing else but the indicator function I subscript A of theta I. And I subscript A of theta I is equal to 1 when theta I is in A, otherwise is 0. So effectively, the sum divided by 1 over n is nothing else but the number of samples that I'm in A divided by the total number of samples. So effectively, if we compute this empirical measure pi hat of A using this mixture of delta Dirac functions, what we get is we get immediately the Monte Carlo approximation that we saw before. And so here is the idea. How about when we want to compute Monte Carlo estimators, instead of using the actual distribution pi of theta, we use this empirical measure defined as this mixture of delta Dirac functions with weights 1 over n. And that's exactly what I'm going to do in the slides that you will see coming up. Let me say before we proceed that the way that I defined this empirical measure, the weights are 1 over n, but later in our lectures we will see that you can define empirical measures with weights that are not equal 1 over n, so not all samples are of equal weight, and we will even see methods that dynamically adapt the weights as you try to approximate certain things. Okay, but for now the weights are 1 over n. Okay, so let me give you a schematic of a Gaussian, and it's this empirical approximation in terms of samples. So you can, this is my Gaussian, and now these are samples drawn from this Gaussian. So the samples alone defined an empirical approximation of this Gaussian distribution, okay? And this is what I am going to try to use from now on in the remaining of this lecture to compute Monte Carlo estimators for integrals, expectations, and the like, okay? Because we saw that when you do these computations using the empirical measure, you do get the Monte Carlo approximations that we have seen before. Now, what is important, and I want you to pay attention, in most of the course up to now, when somebody gives us samples, we always try to fit them parametrically to some distribution. Here actually we are going the other way around. We have a distribution like this nice Gaussian with some given mean and a variance, but now we're going to throw away that parametric representation and we're going to use the samples, and we're not going to go back to the parametric representation. Okay, so I will try to emphasize this again in this lecture, but the samples alone would be used to provide an empirical approximation, a Monte Carlo approximation of the Gaussian distribution that you see. Now, to sort of use your imagination here, suppose that you were trying to calculate some integral of some function f of theta under pi of theta. So this is the expectation that we saw before of f of theta. And let's say pi of theta is some bimodal distribution the way that you see here. If you were to do that integration with your standard numerical analysis tools, you will split the two directions in equal intervals, and you will integrate over each little block. So this is, you need a grid of discretization points delta x and delta y. But when you try to do this with Monte Carlo, you will use the Monte Carlo approximation of this underlying distribution, and because the distribution mass, the mass of this distribution is concentrated here, the samples will look like this, all right, the samples will look like that, and you can see you don't need a grid. The number of points that you use are sparse, and they better represent where the integral, the contribution to the integral is non-zero. So the Monte Carlo approximation looks to me much more natural than using the deterministic approach that you are familiar with. All right, so if you want to calculate the expectation of f under pi, we said already we will, instead of pi, we are going to use the empirical Monte Carlo approximation of pi, which you see here. So immediately this will lead to the integration with these delta functions of f of theta, and this will give you f at each of the samples. Okay, that's nice. So that's exactly the Monte Carlo estimator that we had before. And if you want to calculate the error, the variance, that's you can use the samples to do that. So you remember the variance of our estimator will be the variance of f divided by n, and the variance of f can be approximated as the expectation, the pi of f squared, and the expectation of f squared. But now instead of pi, I am going to use expectations with respect to the empirical distribution pi hat. And this is what I have here of the two estimators. This is the expectation of f squared, and this is the expectation of f squared. Now, interestingly, if you have, let's say, two random variables theta 1, theta 2, and you write the Monte Carlo approximation of the distribution with samples theta 1 and theta 2 as you see here, if somehow you need to marginalize, the marginal distribution immediately is given by getting rid of theta 2i and only keeping these delta functions in theta 1. Now you can immediately guess, right? The reason for that is if you integrate theta 2, the integral over these delta functions in theta 2 will actually give you 1, and what you're left with these delta functions in theta 1 alone. Now, I had mentioned before that we're going to be using Monte Carlo approximations also even to compute map estimates, right, and doing optimization problems. And here is a simple way to see this. Imagine that you have a distribution that now you have a Monte Carlo approximation of it through samples, and somebody asks you what is the map estimate, or what is let's say that is your posterior, and somebody asks you what is the map estimate of that posterior. So what you do is you take the empirical approximation of that posterior in terms of samples theta 1, theta 2, etc. And then the map estimate is the theta I that is the maximum of these samples. That's it. All right, that's it. So we can do marginalization, we can do optimization in a rather straightforward manner. And of course, all of these things require, unfortunately, that we will need to spend a lecture or two to discuss how do we sample from different distributions, especially in high dimensions, because if you cannot sample, then you're in trouble. So let's see another example. Let's say that no probabilities, no apparent expectation. Somebody gives you an integral of some function f of x, and x can be in high dimensions, and tells you go and compute an estimator of this integral. Now you don't panic, right? You look at this, you say, okay, it doesn't look like expectation. Or maybe you say, you know what, it is the expectation under the uniform random variable defined in that domain D. And if that is the case, I can sample n times from the uniform distribution, and my estimator is that what you see in the bottom. And regardless of what the dimensionality of x is, the convergence rate for this will be 1 over n, 1 over square root of n. Okay? That's the standard deviation basically in your Monte Carlo estimator for this integral. Now, if you try to compute this integral by deterministic methods, what you will need to do is, for example, if you try to do this in one dimension, you will need to discretize the interval 0 to 1 in, let's say, in increments of delta x that they are 1 over n, so we can have the same grid of points as for Monte Carlo. And the convergence is, of the order of omega of 1 over n. So in the deterministic problems, the convergence is, in one dimension is better than Monte Carlo, is of the order of 1 over n. But let's see the problem. If you try to put the same uniform grid of n points in, let's say, 10 dimensions, so you would need n points in one dimension, n points in the other one dimension, so you're going to need n to the 10th number of points to achieve the same rate of convergence, this 1 over n rate of convergence. So the number of points that you will get for a Riemannian approximation of the integral, it will be prohibiting. Now, more general, if you need to integrate in some subdomain in high dimensions, let's say d here, the convergence, and I showed you this formula before, is 1 over n to a power r divided by d, where r defines the smoothness of the domain d, okay, and d is the dimensionality of the problem. All right, so this is the general convergence of this Riemannian or deterministic integration approach, where you use a uniform grid in each dimension for a total number of n points. Okay, so I am showing you here on how you're going to do this integration using calculus, right? If you split this in one dimension in a uniform grid of delta x points, and locally you approximate the contribution to the integral as f of xi times delta x, this is what you get, all right? And the approximation error is of the order of 1 over n in that uniform grid of points. But unfortunately, in high dimensions, as we saw, the rate of convergence depends on the dimensionality. In Monte Carlo, there is no dependence on the dimensionality, but the rate of convergence is 1 over square root of n. Now, you may wonder, but is the cost of actually computing samples from a high dimension distribution more expensive? Well, we will need to discuss about these things as we move along, okay? But for now, remember that the Monte Carlo error is of the order 1 over square root of n, and it is independent of the dimensionality of the problem. And again, you see this calculation of the integral of f of x, pi of x. In 1D, you use a uniform grid. In the Monte Carlo 1D integration, you basically have to take samples that they are mostly concentrated where the probability mass of pi of x is, because that's where the major contribution is. So uniform grid versus samples coming from pi of x in the Monte Carlo approximation. Okay, so let's revisit so we can get some numerical results for this integral. So we're interested on this estimator mu of f, which is the integral from 0 to 1 of f of x dx. And we said our approximator will be defined by taking samples from the uniform distribution in the interval 0 to 1. And this is our Monte Carlo approximator after n samples from the uniform distribution, denoted here as m hat subscript n of f. So let me give you, for different values of f of x, the results for this integral. So the actual results are shown here with the values mu, and so you can see here how, as the number of samples changes, how this Monte Carlo estimation proceeds. Again, the true mean here is 0.5, the true mean here is 0.33, and in this particular case on the bottom is mu equal to 0. Now you can compute the variance for this, and because these functions that I showed you before, you can calculate both the mean and the variance analytically. You can do this analytically, or you can do it in terms of samples. So in terms of samples, I remind you, the sample mean is the empirical mean, okay? And the sample variance with respect to the sample mean, again, is given by the expression we have seen before. And remember, I am using the unbiased estimate for the variance, so 1 over n minus 1. So the mean and the variance of f can be computed, and of course you remember the estimator. The variance is the true variance divided by n. So anyways, I give you the approximations here of if you compute the variance of f with analytically by performing the integrations versus this Monte Carlo estimation, you can see how the results look like, okay? And they converge very nicely, and you can start posing simple questions similar to the inequalities that we saw before. So you can start asking yourself, if I want to compute the probability that my Monte Carlo estimator for the integral is away from the true mean, from the true value of the integral by epsilon, and if I want this to be, for a given epsilon, to be 1 minus alpha, how many samples do I need? All right, so that's a reasonable question to ask, okay? So again, by using the values from the CDF of the standard normal, you can immediately you can compute the value that you need to have here by taking the inverse of the CDF computed at 1 minus alpha over 2. Remember, here you have an absolute value, right? So you look at the central interval in the Gaussian to be 1 minus 1 minus alpha. So effectively, on the left and the right tails of the standard Gaussian, you have areas that they are alpha over 2 and alpha over 2. So to compute this, you're going to have to compute the inverse CDF at evaluated at 1 minus alpha over 2. So at the end of the day, it turns out that the number of samples that you will need to have this probability being less than epsilon, for a given epsilon to be 1 minus alpha, the number of samples will have to be greater or equal to the an approximation of the variance of f, and I put this approximation with hat here because I am going to use samples as you saw before to do the evaluation, and x alpha is this inverse CDF for the standard Gaussian evaluated at 1 minus alpha over 2, and that's it, okay? So you can, I am sure you can spend a little bit more time studying this slide, all right? It's nothing but using CDF tables, but it allows you to compute the number of samples that you need for a given epsilon to make this probability to be 1 minus alpha. And by the way, this number of samples that I computed here, when I say I want this probability to be less than that, right, to be 1 minus alpha, n can be greater than this value of corresponding to x alpha that I computed here. So I use an inequality here to say n has to be greater or equal to this estimate. Okay, so how do you actually compute the number of samples to satisfy this? So here is a little algorithm. So you can think, you draw n1 samples from, remember we are computing the integral of f of x dx, let's say from the uniform distribution, okay? So you draw n1 samples from the uniform distribution. Using those samples, you evaluate the variance of f, and you use the samples to do this approximation, and you check if this is less than n1 epsilon squared divided by x alpha squared. If that is the case, then you're happy and you stop. Otherwise, you will have to evaluate how many extra samples you will need to take to make this to happen, and the number of extra samples will be x alpha squared times the variance of f divided by epsilon squared minus n1, where these brackets here indicate the integer part of the number inside the brackets. So you will need k1 additional samples, and now you repeat the calculations, you calculate the variance of the estimator for those samples, and you evaluate this for the total number of samples. If this inequality is satisfied, you're done. If not, again, you find K2, etc., until the accuracy that you are interested has reached the desired level. Okay, again, nothing changes if the problem becomes a high-dimensional integration. The rate of convergence is the same, but as we anticipate, the number of samples that we may need to draw will have to increase for a given accuracy. And of course, there is this extra issue you need to worry, which is to actually take samples from pi of x when pi of x is a high-dimensional distribution. Okay, let me finish with two examples, and it has been a long lecture, but I think hopefully you will find this useful. So I am going to use an example coming from the Bayesian core textbook on computing the Bayes factor. So let's say that we have two data sets, x1 to xn, coming from the distribution that you see here, and another data set y1 to yn coming from another distribution. Both have the same variance but different means, and we want to basically check the following hypothesis if the means of the two distributions are the same or not. So I call the hypothesis H0 for the means to be the same, and H1 for the means to be different. Okay, so now the variance here, sigma square, is the same, but it is unknown. So I'm going to need to be able to evaluate the Bayes factors, because this is how I'm going to compare the two models. I'm going to need to put a prior on sigma square, and I'm going to use an uninformed prior, which you remember it's 1 over sigma square. Okay, so here is the Bayes factor 1, 0, all right, is the likelihood of my data. Remember, the likelihood is written here as a function of the two means and sigma square. And dn here indicates both my x data set and my y data set. This is the prior on the means, this is the prior on sigma square, and the Bayes factor involves marginalization in all the parameters. So I have these integrals in sigma square and integrals in mu x and mu y. Okay. By the way, even though we are using here this prior 1 over sigma square, if in general you use an improper prior in computing this type of Bayes factor, and you use the same improper prior on both the hypothesis 1 and the hypothesis 0, you don't have to worry about the normalization constant, because if it is the same, they cancel out from the numerator and the denominator, and the same is true here using 1 over sigma square. Okay, so that is the fact that we use an improper prior is not a problem. Okay, now we need to compute this integral, and obviously the first thing you may think of doing is brute force Monte Carlo, but actually it would be smart to only use Monte Carlo where exact integration cannot happen. Okay, so in our case we can simplify this, and there is a calculation from Bayesian core that I'm going to take you through it rapidly, and then you can read for the details in the slides and in the textbook. So let me do the following thing. I am going to introduce a new parameterization. I'm going to take mu x to be mu minus xc, and I'm going to take mu y to be mu plus xc, okay? And I'm going to take a prior on mu and xc that it factorizes as you see here, okay? So we're going to use a different parameterization because this will allow us to use basically the same prior in both the hypothesis H1 and the hypothesis H0. Okay, so for mu, what I'm going to do is I'm going to use a uniform prior, and for Xi I'm going to take to be the standard Gaussian. So if you use this parameterization, okay, there is no literally significant algebra, but you're going to have to use the standard approximations for the likelihood coming from a Gaussian model. So I'm going to introduce the notation as x squared, the sum of squares that are the square distances of my data from my MLE estimate, and I'm going to do the same thing for the SY square. So if you use the standard ways to approximate the likelihood, the Bayes factor 1, 0 can be written in, let me concentrate, for example, on the denominator. What you're going to have is the likelihood for the X data. And you notice I have approximated the likelihood in terms of Sx square, and this square error of my true mean, this mu from X bar. Literally, there is no algebra here. Take the exponential of in your Gaussian likelihood of summation of xi minus mu squared, right? And add and subtract x bar and expand, and this is what you will get for the x data. This is what you will get for the y data. They have the same sigma square. The prior on mu is uniform, and the prior on sigma square is 1 over sigma square. And then I'm going to have the same type of calculations on the hypothesis 1, okay? And notice these formulas on the numerator will look, slightly. So in hypothesis 0, both both Gaussian distributions have the same mean. In hypothesis 1, they have mu minus xi and mu plus xi. So this is why the likelihood terms look different. There's really, again, there is the same way that I got a calculation on the denominator, you can get the calculation in the numerator. The only thing, instead of x bar here, use xi plus x bar. In terms of y bar, use y bar minus xi. Okay, and this is how you get the equations on the top. Now you're going to introduce a new variable to allow you to simplify this Bayes factor. So I'm going to introduce this capital of S square that involves Sx squared and Sy squared divided by n, and this way the Bayes factor can be simplified significantly. So what I have is a simplification of the this exponential by using this S square. So the Sx squared and Sy terms have been combined. Then I have my prior on Xi, which you remember is a standard Gaussian. The prior on mu is equal to 1. Okay. All right. So the question is now, can we do the integration on sigma squared exactly? And the answer is yes, you can. All right. So you need to to be careful on how you do this. But if somehow you are familiar with the student t distribution, okay, you can integrate sigma square out, and this is exactly what I have done here. So it seems to me sigma squared has been completely disappeared, and what is left is an integration on mu and an integration on Xi. And actually this integration on mu, okay, the integration on mu can also be done analytically, and so let me give you the final result. And actually I referred before to the student t distribution. I was a little bit ahead of myself. So if you do the integration on sigma square, and notice sigma square comes here, and you have e to the minus something divided by sigma squared. To me, that reminds me the normalization factor of a gamma distribution, okay, not of a student t distribution. So if you do the sigma integration, you get this to the power minus n, and that now reminds me a normalization factor of a student t distribution, and that's exactly what I have done here. If you do the normalization in mu, you get the normalization factor of a student t distribution that I remind you here what it is, okay? And at the end of the day, certain things cancel from the numerator and the denominator, and this is what you get. I have reversed here the Bayes factor just for convenience. What you see is the B01 Bayes factor, so 1 over what we had in the previous slide, but the integration in mu has been completely done. Remember, in one of the terms there was no xc because the two mu's were the same. In the other there was a xc that you can actually appreciate here comes from a Gaussian distribution. This looks like, and it is, an expectation under the standard Gaussian. So you can imagine what the algorithm will be, right? You take samples from the standard Gaussian, you do a Monte Carlo approximation of this long integral, and that is the approximation of the Bayes factor that you see here. It comes up, if you take one set of samples, the value is 43.33, and actually you can repeat this by taking multiple times 100 samples from this standard Gaussian, and if you do this, you can get actually a histogram of the Bayes factor, and so you can discuss about error bars and other moments as it is of interest, but also you can use the Monte Carlo approximations that we discussed before for computing the integral, but somehow you have to be careful because you notice here your estimator, the way that I have it is this constant term here divided by this denominator term here. So your Monte Carlo estimation is going to be going on the bottom. So generally when you have the ratio of two Monte Carlo approximations, you need to be careful as to how you evaluate the error in that ratio. So to avoid having to discuss this, here you can just live with this picture where the calculation is being repeated. So for each calculation of the whole Monte Carlo procedure, you compute the Bayes factor, and then you plot a histogram that looks like this, and that gives you the mean, gives you the variance, and everything else you want. I think I have one trivial example in one slide, so let me just spend 10 seconds to go through this. This is an example where you want to calculate the mean of a Gaussian, okay, given standard deviation, and the idea here is you have a sample X from this Gaussian, and you want to compute the mean, and you put a prior, a robust prior that is a Cauchy prior. So, and you want to compute the posterior mean of theta. So what I have here is theta from the expectation from the posterior mean times the likelihood, which is this exponential, times 1 over 1 plus theta squared that comes from the prior. And then I have the normalization factor in the denominator. So effectively, you can immediately see that you can do this both integrals by taking Monte Carlo approximations of the numerator and the denominator. So the posterior mean estimate with Monte Carlo is given by this ratio. Again, I will advise you to be very careful when you compute the error when you use ratio of Monte Carlo approximations, okay? So, but certainly numerically, you can evaluate this for repeating your Monte Carlo estimation and then plotting a histogram of the results. And in some way, the plot that you will see here is doing like this. And so that's the posterior mean. And that's another example of using Monte Carlo approximation. Okay, that's all on this very long lecture. I am going to stop here, and we will continue with Monte Carlo approximations in 2 days from today. Bye.